talk a little bit about friction loss now. Head loss is created by the friction of the water flowing through a pipe. Head loss is a term that means how much vertical potential, pumping potential, are you losing. It means, let's say a pump can pump 20 feet vertically, but by choosing piping that's a little smaller, you may create friction that would only allow that pump to pump 10 feet. Well, you would have 10 feet of head loss because of the friction created in that example. So this is a function of velocity, a friction factor, the length of the pipe, the diameter of the pipe, and gravitational acceleration, which is a known value and it's a constant. So this is figured out by the Darcy-Weisbach equation. This is H equals F L divided by D times V squared over 2G. And that's friction factor, length of pipe is L, D is the diameter of the pipe, and then we multiply that by the velocity squared times 2 times the gravitational acceleration, which is 32.2 feet per second. So first we have to calculate F. To calculate F, we have to calculate the Reynolds number, which is another calculation here, then refer to a Moody diagram showing the friction factor in relation to the Reynolds number, okay? Getting a little tricky here. Reynolds number equals Vd over lowercase v, where the v is velocity, the d is the pipe diameter, and then v is the kinematic viscosity, which is another known number, okay? The Darcy-Weisbach calculator for head loss and pressure loss is right here. So if you want to go on Engineering Toolbox, we can actually look at the Reynolds number. We can come up, look at a Moody diagram, and we can come up with this number, a hard number. But that's a lot of math to constantly do for every single problem, every single friction loss problem that you're going through. There's a lot of these calculations that happen in designing a system. So there are known and made calculators that already have this information put in, and all you have to do is enter in your specific information and it will spit out the answer and tell you how much friction loss you have. So this is gold. Remember these two sites here, these two links. You can get all of your questions answered on friction loss by entering the known values that you have, and it will give you the friction loss and allow you to make good decisions. There's also the Hazen-Williams formula is also widely used, so Darcy-Weisbach and Hazen-Williams, both widely used, but both come up with a correct number for friction loss. This is one more very good link, and this is from Spears Manufacturing, which is a big manufacturer of plumbing pieces, PVC, and they have a lot of data on that. So I would suggest checking out that link. There's very valuable information on plumbing and system design from people that are manufacturing these plumbing fittings. So I would recommend you take a look at that link and save it in your good file box. So here is a friction head loss chart from Engineering Toolbox that we copied in here just so you can get a visual representation while we're teaching this. And it gives you the diameter of the pipe here, 3/4 all the way up to 6 inches. It gives you your gallons per minute on this vertical column. And then it tells us how many feet of head loss per 100 feet of pipe. So let's take a look at this at, say, 20 gallons per minute. If we're using 1-inch pipe, pumping 20 gallons per minute, for every 100 feet of 1-inch pipe, we're going to get 21 feet of vertical head loss that we're going to lose just due to friction. Now, if you go all the way out to 3-inch pipe, same flow rate, you're going to get 0.1 feet of head loss for every 100 feet, which is basically nothing. You're not getting any kind of friction loss through that pipe. 2-inch pipe, you get a little bit more. But once you figure out what size pipe and what velocity you're shooting for, which chooses the pipe size, then you can see right here what the friction loss is for all your distances of straight pipe, so all the straight lengths. Using that chart, this is just a quick example, wants you to calculate the friction head loss at 40 gallons per minute using 50 feet of 1.5-inch pipe. Well, 40 gallons per minute, looking at that chart, through 1.5-inch pipe is 9.5 inches of head loss for every 100 feet of pipe. So 9.5 inches divided by 2 equals 4.75 inches of head loss for 50 feet of 1.5 inch pipe. 4.75 inches can be the difference between water flowing through your system and water overflowing the fish culture tank, because you don't have enough head pressure to drive it through the mechanical filtration and the rest of the system components. Do the math first, then do it again, then cut and glue the pipes. I've told myself that my entire career. I've still cut many pipes that were too short, too long, you know, not the right size. And it's always the piece of pipe that you only have one left of, or the last T-fitting, etc. So do the math, do it many times until you're sure it's a hard number, and then go out and do your project. I'd rather waste the time in here than waste the money out there. So here's another calculator for you. It's a shortcut. Instead of having to look at some of those tables, this engineering toolbox link will be very helpful. These tables have values for friction loss and velocities up to 16-inch pipe. So you can actually look at your flow rate and the type of pipe, and it will tell you the velocity, the friction loss, everything you need to know right here. Lets you skip all those equations, all that hard stuff that all the non-math people don't want to do. This is your magic button right here. So utilize that. These are solid numbers created by engineers that are ready to use. You can trust them. And here's another calculator where you can actually input your information, and it will tell you the velocity or the friction losses within that system. So again, take the time to click on these links and check them out. I'm not associated with them, but I've used them for years. They're great information. So here's an example chart off of that last link for 1 inch Schedule 40 PVC. And they have several different types of PVC, different types of piping. Schedule 40 PVC is the standard PVC that we're going to be plumbing with in our aquaculture system. I'd say anything 8-10 inches, 12-inch piping and under. When it gets above that, you change materials. So 1 inch pipe, we can see you've got the volume of flow, and it tells you gallons per minute or gallons per hour. So 2 gallons a minute equals 120 gallons an hour. That velocity of that in 1 inch pipe is 0.8 feet per second. Friction per 100 feet is 0.6, and the friction loss, let me see here, in PSI is 0.2 PSI. So 27 inches of water depth equals 1 PSI. So it's just giving you the loss in a different term here. But what does that tell us? So let's say we wanted to do 10 gallons per minute and we wanted to do a gravity line. Well, a gravity line going through here, 10 gallons a minute, we're going to be at 3.9 feet per second in 1 inch pipe. So we're going to be at 3.9 feet per second in 1 inch pipe. And that's too fast. For gravity, we want 2 feet per second. So that tells us 1 inch pipe is going to be too small. Look at the next table for 1.5 inch pipe and see what the velocity is there. If that's too low, look at 2 inch pipe. So right here, you can just look at your velocity. If you know your feed amount, you know the culture tank size, you know the fish amount, we figure out the water velocity that we need, we already have it here. Then all we have to do is look over and it will tell you the correct piping due to the velocity, whether it's a gravity or a pressurized line. So I hope that really made sense, because these charts tell you everything that you need to know, even for large system design. But that's all for straight fittings, straight pipe. But we still need to calculate the friction losses going through the fittings, all the elbows, T's, bulkheads, entrances and exits of piping. All that needs to be accounted for and added to our total head loss. And that calculation is right here. H equals K times V squared times 2G. H is head loss, K is a coefficient that we're going to get given on the next slide. V is the velocity, which we're going to know, that's our pipe velocity. And G is 2 times the gravitational acceleration, 32.2 feet per second. So here's our K values for the PVC fittings. You can find these K values on Spears Manufacturing website, on other PVC manufacturers' websites. These I actually took out of Recirculating Aquaculture, the book, for you. I just went ahead and we've got the table right here. But it gives you 90-degree elbows, 45-degree elbows, T's, gate valves, swing check valves, ball valves, every type of fitting that you need, and then all the way up to 16-inch fittings. And it gives you the K value, which is going to relate to how much friction you're losing through that piece of equipment. So for this example, we want to calculate the head loss of 100 gallons per minute flowing through 5 3-inch 90-degree elbows. H equals K times V squared over 2G. So calculate the velocity. We did that in one of our earlier problems, and we're just going to use that same velocity of 4.23 feet per second. And we want to find the K value for 3-inch 90-degree elbows, for 5 of those, like we said right here. So by doing that, we say H equals the K value, which from the table is 0.54, times our velocity, which was already known, velocity squared, and then we divide that 2 times 32.2 feet per second. That's our 2 times our gravitational acceleration. Right back to that formula right here. H times V squared divided by 2G. And this gives us 0.15 feet of head loss per fitting. So multiply that by 5 and we get 0.75 feet of head loss. So 0.75 feet of head loss just through those 5 elbows. We add that to the head loss through the straight pipe and we get our total head loss. Okay, well, I guess I should correct myself. We add that to the length of straight pipe, but that was just for the elbows. So we do that for every component in the plumbing schematic. All the T's, the bulkheads, everything we saw in that K value sheet. We want to go ahead and do the friction loss for all those fittings. So we add all those up, then we add that to our length of straight pipe, and that gives us our total friction loss throughout the entire system. Now, a lot of times you need to calculate the friction loss between 2 components, not necessarily from the beginning to the end. You need to make sure water flows from the fish tank to your first stage filter, from your first stage filter to your second stage filter, and so on. So it's important to do these calculations through each section. Make a nice little drawing, just draw it out by hand, and then write it out so that you know how much of a drop you need between each component in the system. Total static head equals the height difference between the water level in the sump, so the lowest point in the system, and the highest point that the water's pumped to. That's the total static head. So water's down there, we're pumping to here, that distance is static head. Total dynamic head is the sum of the total static head plus your friction head loss through all that pipe and the head loss through all the fittings. So we can say the head is, let's say we're pumping 10 feet, it might be 10 feet of total static head, but after you put in all the resistance, you might have 14 feet of total dynamic head, which is what you're going to need to overcome to pump the right number into your, the right volume into your culture tank. And this equation is TDH equals H stat plus H pipe plus the sigma H fittings. But your static head pipe, pressure loss through pipe, pressure loss through fittings. A lot of letters, actually really easy. And this is just a quick picture to give you an idea of what I'm talking about. So our head pressure is going to be from, let's say this is completely full of water, from this point to the water line in this tank. Even though the pump is going to pump up here, over, and down into this tank, it's this distance, not this distance. This distance is our calculated head pressure. So, our total static head. When we look at the next slide, this distance here, these are actually opposing forces that cancel each other. So gravity is making the water fall in this pipe, and that is actually pulling the water up this pipe, similar to a siphon. So these forces cancel out, and those are not included in the calculation. But what is important to know is that your pump needs to at least be able to pump to that maximum height to let the water flow over and back down. If it can't pump to that maximum height, even if the head pressure is, say, 10 feet, if it can't pump to the 14 feet to have 10 feet normally running on the pump, then the pump's not going to ever flow water. So that's a very important thing to keep in mind when we're looking at pumping systems. So moving on to mechanical filtration, which again we've talked about a little bit now. It is installed immediately after the culture tank for quick removal of solids. Best to gravity flow into this vessel so we don't macerate the solids. Don't pump the solids into the filter because you're just chopping them up with the impeller and making smaller solids, and the smaller the solid is, the harder it is to actually pull out of the water column. And there's many types of filters on the market to achieve this goal. Swirl filters, baffled clarifiers like the University of Virgin Islands, radial flow settlers, upflow media filters, microscreen drum filters, incline belt filters, sieve filters, and bead filters. There's a lot more filters out there, but these are the ones I'm going to talk about. So here is a drum screen filter. This is, was actually in operation on the rooftop greenhouse where I used to manage. And this is a Hydrotech drum screen filter. And in this picture you can see this blue tank is actually, the water's flowing this way through the system. And this is just a collection tank. It's actually a standpipe well is what we call this. And all three of the 1,500 gallon culture tanks, because they were at different distances away from this, they're going to have slightly different water levels if we had them all coming in at the same pipe because of friction. So the water's going to flow the path of least resistance, and as a tank gets further away, it's going to take more head pressure to flow it here by gravity. So in order to control all three of the tank levels independently from one place, we use this tank. So there's actually 3 inlets into this tank, one from each of the fish culture tanks, and it simply allows us to set an external standpipe on that tank and set the water level, and all the water from all 3 tanks collects here and then flows through one main pipe into the drum screen filter. So very small footprint and very efficient way to install. As this water flows through the screen, the clean water falls through the screen and into this system, which is the sump, and is returned to the culture tank. The dirty waste is captured within that screen, and as the water rises, because the screen is filled up with particles, it triggers a switch that causes the entire screen to rotate and high pressure sprayers on the top to spray the screen clean. So the screen's rotating and water is spraying straight down on that screen. Well, it dislodges all the waste into a central drain pipe, which is right here. So all of your sludge is dislodged and it's sent out of that drain pipe and out to a sludge collection area. Very easy to use, very small footprint, but that gives you an idea of how it works. And we're actually going to talk about 2 studies here on mechanical filtration that are very important to compare when we're looking at what do we want to use for our first stage of mechanical filtration. And these 2 studies compare the effectiveness of swirl filters, baffled clarifiers, and radial flow settlers. A comparative study between all 3 filters under the same conditions at the same time under both cold and warm water conditions has not been done, but we can draw conclusions from these 2 different studies. So we're going to look at the clarifier versus a swirl separator versus a radial flow separator. So these 3 different first stage mechanical filtration devices, and we're going to compare them, their efficiency, and see which is the best choice for us to use in our system. The first picture here shows the University of Virgin Islands baffled clarifier. So this is a large cylindrical tank with a 45-degree cone bottom, and as you can see, the water enters the tank through the sidewall at a 45-degree angle up, so that the water has to travel up and then travel back down, helping to dampen the flow a bit. As it travels down, it goes under the baffle in the middle and back up through the outlet here. By doing reversal of direction, the solids that are heavy will actually drop out and settle in the bottom of this cone. Again, the clean water will go up and go out of the outlet. There's also another small baffle located near the outlet, and that's just in case any of this goes anaerobic and some of the solids float to the surface. They won't go out of the exit pipe. They will actually get trapped behind that secondary baffle. And here is a valve, so when you open the valve, it will suck the waste out of the bottom of that cone and deliver it into their waste pond. Next here, we're going to go ahead and look at a swirl separator. And this is the cross-sectional diagram, so we split it in half just so you can get a look at the internals. And if you look at where the water inlet is, it's right here. And it says a tangential inlet. So the water is being flown in a tangential direction so that it swirls around the filter, creating a flow that draws solids down into the center of the bottom of that cone. So you'll see at all of these, the purpose is to grab the solids and get them to the bottom of the cone there so we can remove them easily. So the water swirls, the heavy solids are moved to the bottom of the cone, and the clean water spills over this sawtooth weir here at the top. So it falls over that weir and it goes out of the exit there. This is a radial flow separator. So you can see it looks very similar to the last picture that we looked at. But instead of coming in at a tangential direction and flowing in a circle, we're coming in straight, and we're actually going straight up with a 90-degree elbow. And we're going to create a radial flow within this vessel. The water comes up, and then it's immediately into a wider pipe there. So the velocity is slowed down. So that's our first stage of velocity slowing. And then as the water goes down, it moves into a wider vessel here. So velocity slows again, and the water has to change direction again and go back up. Well, by doing that, we have drastically changed the speed of the water from this small inlet pipe to when the water's moving upwards to spill over this outlet weir. And by slowing the velocity, we allow those heavy solids to settle out in the bottom of this vessel. So again, it's very easy to see how this works. The water comes in going upwards. By gravity, as soon as it goes up, it's going to have to turn back down because this comes up and the top of the water is right here. So it comes up, hits the surface of the water, has to turn around and go back down, and then it has to turn around and go back up here again to go over the weir and flow out of the vessel. So there was a study done by Charlie Schultz, Jason Danaher, Dr. Ricosi, Dr. Bailey, down at University of Virgin Islands, so this is the UVI team, and they compared their clarifier to a swirl separator. And the abstract is in Aquaculture America 2011, if you want to take a read of the entire abstract. So what the end result is, they found no scientific difference between the total suspended solids concentration in the effluent of the filters, meaning statistically, there was not a big difference in how many solids were removed by using these two different filters. But in reality, their test showed that their clarifier actually removed 58% of the total suspended solids, and a swirl separator only removed 48%. So in reality, they did have better results with their clarifier, but to be scientifically significant, it has to be above a 10% margin there. So next, we're going to look at Steve Sommerfeld and Mr. Davidson here that compared the swirl separator and a radial flow filter on a cold water recirculating system. So right off the bat, this is the thing to consider. Dr. Ricosi and the UVI team did their tests in a warm water tropical environment system. This is in a cold water trout system. So the water temperature does have an effect on how solids settle and what your total suspended solid concentration is going to be coming out of these filters. So they're not exactly apples to apples, but again, we can compare both tests here at the end. Here they compared a radial flow separator and a swirl separator. Well, the radial flow separator showed a significantly higher removal efficiency. In the swirl separator, they removed about 37.1 total suspended solids, or 23% of the total suspended solids removed from the system. The radial flow separator was actually closer to 48% of the total mass of total suspended solids removed from the system. So that's a huge difference there. Same flow, same treatment, but actually a much better removal efficiency out of a radial flow separator. So when we look at all three of these tests, we have to draw conclusions. So the University of Virgin Islands says there's not a huge difference between swirl separators and the baffled clarifier, where this other test says there is a very large difference between a radial flow separator and the swirl separator. So out of the three, I would choose the radial flow separator as your primary solids filtration device. And that's going to be industry standard throughout aquaculture. That's what is used at the majority of facilities out there. So we'll go ahead and talk a little bit about that. A radial flow settler, like we just said, is the current industry standard. And then they also, by having a first stage, it increases the efficiency of your second stage. So let's say we were using a drum filter that is going to pull solids out down to 60 microns in size. Well, we could obviously send all of our solids directly to that drum filter. And because it has 60 micron screen, it's going to capture all the large solids as well as those fine solids and wash them out. But the difference is you have a lot higher discharge of water if that drum is constantly rinsing and constantly backwashing all of the material off of the drum. So by using a first stage radial flow settler, we can concentrate solids without using a lot of water to rinse that out constantly, and just do one massive flush every time we're disposing of that waste. Micro screen drum filters are aquaculture industry's standard as a primary or secondary solids removal device, but they're not heavily utilized in aquaponics right now due to the cost, the water usage, and the project sizes. So there's just not a lot of huge aquaponic projects happening yet. The numbers are growing, but the smaller operations, the family farms, there's by far a lot more of those right now in the world than there are large-scale industrial size operations. But as scale grows, microscreen drum filters will be utilized heavily in the future of this technology. In this slide, we have some extremely large radial flow settlers, and you can see this little guy here in orange, that's a person, but it's very big but very easy to see exactly what we just showed in that cross-sectional diagram. There's an inlet underneath here, it goes into the stilling well, pointed up, the water goes up, the velocity is dampened as it goes back down, and then the velocity is again dampened as it changes direction and comes back up over the sawtooth weir and then out of the outlet there onto their next stage of filtration. A second stage of mechanical filtration is generally required to remove the other 30 to 50% of the solids that are left in the system after this first stage of filtration. So that's the microscreen drum filter that we just talked about. That's a static screen system, so meaning on a smaller system you could actually use a piece of screen, static, have the water fly over that, and then once, twice a day, whatever your cleaning regimen needs to be, you actually physically spray that off and then put it back into use. We could have a bag or mesh filtration. We could have netting filter, just like University of Virgin Islands uses, or we can have an upflow media filter, which is what I actually use at Chatterson Farms here. Here's a picture of the orchard netting tank at University of Virgin Islands, and you can see the water comes in and actually flows this way. So these are long rectangular tanks. It's going to flow all the way through the body of that netting and out the other side, then back through another tank that's just like that. So there's a long contact time and a long exposure time to this netting. And as it fouls a little bit, it actually grabs some of those other small particles. So just as particles start to attach, they attach to other particles and grow larger. So it actually helps to cling to more particles as it gets a little bit dirtier. Retention times are very important for proper solid settling. So in a radial flow settler, in any of these tanks, if we have too high of a flow, the solids are going to stay suspended in the water column and just pass right through that vessel. The slower the flow we have, the smaller the particle size we can actually get to settle out within that vessel. And that's really what we want. But we have to balance how slow the flow is, meaning how big the vessel is, with how much money it's actually going to cost. The primary mechanical filters bought from a supplier will be sized based on flow rate. So they're going to say, okay, your flow rate is 20 to 30 gallons per minute. That's this size radial flow settler. That's how you will purchase that unit. A drum filter or a belt screen filter, which we'll talk about what that is later, those will also be sized on your daily feed input and the desired particle removal size. So 30 microns, 60 microns, 90 microns. How small of a particle do you want to filter down to? And they will actually install that size of screen in the filter as you get it. And that's it for this session. Again, if you have any questions at all, please email me, ryan@collegeofaquaponics.com, and I will be sure to cover those questions in our weekly question and answer session and make sure you get all the information that you need. Thank you very much.